So, okay, but let's go ahead and let's start with the scientific program. And we are a bit ahead of time, but it's good because then we have more time to change. And so this is the first keynote speaker, the first keynote lecture. And it's my great pleasure to introduce our speaker today, Fei Sha, Professor Fei Sha, who is now at Google Research, but he used to be in academia for a very, very long time. So Fei received his PhD from the University of Pennsylvania in 2007. He was in Yahoo for a year, and then he moved back to academia to the University of Southern California, USC in Los Angeles, where he was an assistant professor, associate professor, chair professor, distinguished professor, and he was there for many years. Then he wanted to move back to industry, first to Netflix, where he was director of machine learning research. And since 2019, he has been at Google Research, where he is a manager, he's a research scientist there. He heads a group, interdisciplinary team doing scientific computing, doing AI for weather and climate. Fei is a computer scientist and a machine learning researcher. He has many pioneering contributions in NLP, in computer vision, multimodal learning, representation learning, many fundamental results in representation learning. But in the last few years, he has, like many other ML researchers, he has moved more in the direction of applying ML and AI techniques for scientific computing, for weather and climate, and you're going to hear a lot about that. Now, for his work, Fei has received numerous awards and recognitions. He was a Sloan Fellow. He also has Best Paper Awards in NeurIPS, in ICML, and many other achievements. So we are truly delighted that you accepted our invitation to come here to Zurich and to PASC, and we are really looking forward to your talk today, which is about machine learning and how it accelerates scientific simulation and scientific computing. So without further ado, Fei, the floor is yours.
Wow. Thank you very much, Sid, for the very kind and generous introduction. It's an amazing audience. Zurich is one of my most favorite European cities, and this is one of the cities I frequently travel to. Besides this, warm feeling coming back to this city, and in front of this esteemed audience of researcher and scientist and engineer, I'm humbled. I am who would you call an outsider. I've been a machine learning researcher for a long time, and as Sid mentioned, in the past 3 years, I've been at Google Research leading this team and starting working in AI for physical systems, particularly in dynamic system with the application focus towards weather and climate. It's new, and it's barely 3 years. So I've been learning, and during these 3 years, I learned a lot. And when I received this invitation, I feel like, I'm going to give you this talk. But for some subjects, I just started learning. What should I do to avoid being sounds shallow, pontificating, or arrogant? So I decided, after receiving the invitation, I decided to study the conference. I read the theme. I think Kate mentioned a few things, but I want to highlight a few words. Grand challenge, combining physics and machine learning, and interdisciplinary problem in science. I look at this, I thought, this is something I knew, and I've been very passionate about, so I'd like to share with you. So my goal for today is to tell you about and discuss with you about exciting, cool machine learning ideas. Meanwhile, I also framed this and view this presentation as an opportunity to open the door for me to learn more things from you. So I invite you to grab me when you have time to tell me what are you excited about and how machine learning AI researcher should be focused on, should be working on in this space. To do that, I'd like to start with a bit of a journey myself. I know Sid had a mid-introduction. I've been in this research for about almost 25 years. They make me pretty old. It's quarter century now. And from graduate student until now, I always worked in AI and machine learning. I'm always interested in statistical method. But more importantly, I'm also interested in how this method can be applied to real-world problems. And what I didn't know and I only came to know about 3 years ago, something I worked on 20 years ago that had something to do with the Swiss and also to do with scientific machine learning. This problem is called nonlinear dimensionality reduction, and you can see this. This is a simple object. It looks like a Swiss roll, and it's a 2D intrinsic 2D object. And what you want to do is take a point on this Swiss roll, sort of flatten them out and restore them into the 2D, because originally it's in the 3D space, right? And this is the problem that with many machine learning researchers have worked on, including myself about 20 years ago. You were wondering why such a small toy problem? It's so easy, right? Why is it interesting to the real world? It turns out it is. And from a statistical machine learning point of view, modeling high-dimensional random variable is a very challenging problem. You probably heard of the term curse of dimensionality, and you need an exponential number of training data points in order to fit into high-dimensional statistical model effectively. And if you can reduce the dimensionality, then you can make a progress in terms of the sample complexity. And besides that, reducing 2D or 3D allow you to do exploratory data analysis. You can visualize data, understanding the processes and the relationship among the data point. Obviously, there's a computational saving out of this. This is something where I worked on almost 20 years ago, even at that time, which I didn't know. I didn't have the foresight today working in the weather and climate space. I even did very simple stuff of predicting the temperature on the Earth by doing a linear regression using nonlinear transformation of the data points. And it turns out to be, yes, by large, the point here is linear relationship. Okay. That's 20 years ago, so I don't know whether that's still true in my today's scientific view. Now, 20 years later, I do want to solve a real-world problem, and particularly in the case about understanding and modeling complex time-dependent systems as those exemplified in weather and climate, and because weather and climate has a huge societal impact to our lives. As you know, numerical weather prediction is something has been driving computing technology for the past, ever since the computer was invented. I know many of you probably recognize this guy, the second from the left. His name is von Neumann. He was one of the driving force to advocate advanced computing architecture in order to do weather and climate modeling. And in fact, in 1950, this is the first numerical weather prediction was made by him and leading an interdisciplinary team and made the first numerical weather prediction in 1950 using the first electronic computer at the time. Okay. Numerical weather prediction is an interesting problem. Right? It's recently, people have been talking about it in the community as a quiet revolution. It's a revolution, but it's quiet. And this is the plot from ECMWF. It shows the predictive scales is on the vertical axis, and horizontally is the year. Right? So the predictive scale has to be typically above 70% in order to consider forecast system is useful, and different color indicate a different lead time. The more lead time you have, the more accurate forecast you can have. And this plot actually shows a very interesting trend, and that's why it's called a quiet revolution. During the last, since 1985 until now, if you plot out this, you realize that the improvement has been made through numerical weather numerical simulation of physics-based simulation. You can make an improvement about 1 day lead time per decade. That's why it's a revolution. It's a huge amount of computational effort and a lot of insight in the physics, in statistics, in order to make this improvement, but it's still 1 day per decade. Okay. On the other end, this is a team member on our team actually plot out this. Since 2022, there's a wealth of AI models or AI-based weather forecasting system has been rapidly maturing. Right? Since 2022, in barely a few years, less than 2 years, all these AI-based systems now have surpassed the operational weather forecasting system. Okay, there's some caveats to that statement, but nonetheless, the speed of making progress is huge. So if we step back, think about it, okay, 1 day per decade and 2 years progress. We can ask this question, exploring question: can AI, machine learning technology have a huge impact to other fields other than weather and climate? I hope this presentation try to address some of the, or answer some of the elements of this big question, and by examining the capabilities and or limitations of today's machine learning technology. Okay, before I go into detail, I would like to give a shout out to our teams and the collaborators. This is the multidisciplinary team. It consists of a meteorologist, applied mathematician, climate scientist, computational physicist, and computer scientist like me. So it's a big team, and we work very closely with each other. And by doing these interdisciplinary collaborations, we're able to learn from each other and make quite a bit of a progress in this space. Okay, this talk is based on a subset of our work in machine learning methods. So I'm not going to talk about a lot of simulation work, but nonetheless, they are the background of our work. But instead, in this presentation, I will focus more on the machine learning methodology. I'm also not going, due to time constraint, I'm not going to go through all the details, but I'm understanding the slides will be shared and people can discover all the nuanced detail in those papers. Okay. Now, let me step back to set the theme, what I want to think about and talk about. In scientific machine learning, there's always this nagging question. How much should we rely on physics and equations? How much should we rely on the data? There seems to be a competing opinion. As machine learning has developed such a stage, people may want to say, yeah, we probably don't need equations anymore. Why don't we just building a gigantic simulator? Let's build a data-driven model of the world and everything should be fine. And we can use the relationship discovered or implied in those data-rich models and to drive our future progress. So I had this analogy thinking about how many apples Newton has to see in order to say he actually understands the gravitation law. Just point out, this was actually generated, not actually. I didn't paint it. I actually, to be honest, I could have painted much worse than this, but this is not too bad. Okay, so I'm going to talk about 3 projects reflecting my thoughts and our team's thoughts, how these thoughts has been reshaped and shaped our future directions. And this is the new field. Everything will be changed in a few years, and I think this community, many of you will have to shape the field, and I'm looking forward to hear about it. But nonetheless, I'll talk about 3 projects. Each one of them going to be very brief, and I'm not doing the justice to all the great work my co-author have been working on, but hopefully give you a flavor about our thinking and our perspectives. It's a bit of a subjective, and it's also come from my personal view being actively shaped in the last few years. But let me start with the first one. How well can we learn from data without assuming a lot of things we know about physics or equations, or other way, assuming very little knowledge about physics and equations? Okay, I'm going back to this old problem that I mentioned I studied 20 years ago, dimensionality reduction or reduced order modeling. Now we're given some observations, presumably very high dimensional, that's characterizing the underlying system. And there's unknown processes behind these systems. What we want to do is come up with a latent representation, let's say theta, and the reason current theta will be known later on. We want to do time stepping in this latent space. The rationale is maybe the original space is too complicated, too computational intensive. Let's try to save some computation by doing that in the latent space. But there may be other considerations. But what kind of representation we want, right? This is from get-go, it would be a yield-defined problem unless we put some structure to the modeling assumptions. So we probably want to say is we want this representation preserve the observations faithfully. That means that if we actually have encoding information into latent space and later on when we time stepping and decode it back, we want this encoder-decode pair to be highly accurate. What does it mean to be accurate? Okay, we can think about this problem. We also want that this latent representation not only follows snapshot at the different time points, encoding, decoding correctly, but also follow some real dynamics. What does real dynamics mean, right? We want to time stepping into long horizons so things doesn't blow up. And I think blow up is a very common word used in scientific machine learning, just representing your emulator starting to give you a bunch of NNN, not a number errors, right? Or gigantic things that's unphysical. Okay, this has been a recurring theme to think about it. What does accuracy mean? What does blow up mean? And depending on how to interpret these two concepts in context of machine learning, then we can come up with different ways, different models to try to understand, to model the underlying systems. Okay, let's give an example. So suppose we have this, unknown observation, these observations going through this wiggly dynamics. So the traditional way of reducing dimensionality, reduced order model is focusing on reduced dimensionality, but there's no guarantee in that the latent space, you can have a very nice dynamics to work with. If we're unlucky, we end up in a dynamics like a lot of wiggly things like this. Now, all of a sudden, we have to, in order to do time stepping, we have to use very small time steps. Now, overall, the computation cost will be higher. This is actually going to defeat the whole purpose of doing reduced order modeling. On the other hand, it would be nice, right? If we have a straight line, then we can make a gigantic time step, and this will reduce computation cost quite significantly. But how do we know we get there, right? Well, how do we build this, sort of a desired property into our modeling? Okay, so our approach, this is our actual first scientific ML project, focused on just introducing two ideas and put them together. The first idea is something probably no stranger to people in this audience. It's called neural implicit representation. And this idea goes back many years ago and most recently been revived through scientific machine learning work like PINs. The idea is fairly simple. Let's use neural networks parameter to represent the underlying field. Okay, so now instead of looking at those field variables, now we're going to have neural network parameters here, and then we have a decoder look at the parameters, then it's going to generate the system state. Okay, that's implicit representation, become very popular in computer vision, graphics, and many others. Now, the second idea is thinking about if we actually do time stepping in this latent space. That means that we have to evolve this neural network parameter. So how do we actually evolve them? What kind of mechanism we should have? What kind of dynamic model we should build around the neural network parameter? For this, we're going to use this idea called the neural ODE. And it's also a machine learning work appeared a few years ago. The idea is learning an integrator to evolve this some systems, dynamic systems. Okay, why we want to do this? By doing this, we are thinking of we're going to get a smooth dynamics. By using a neural network implicit representation, we're going to get a powerful expressiveness. We can model any arbitrary snapshot very accurately. We can learn the encoder-decoder efficiently. But that's actually didn't happen. It took us quite a while experimenting with all kinds of architectures, all kinds of learning algorithms. Eventually, we realized that not only we have some ideas, we also need some tricks. We need some secret sauce. We end up having 3 of them. We have to use and customize the loss function to learn encoder-decoder pairs first, instead of learning encoder-decoder plus the dynamics together. We have to do a multi-stage learning. We have to come up with a customer-designed decoder. In this case, it's a nonlinear Fourier ansatz network to representing the state variable. Okay, and this has to tailor the different flow problem. And finally, we also need, in order to learn the dynamics in the latent space using NeuroODE, we have to customize the architecture underlying the NeuroODE with a very special type of neural network. This is actually inspired from UNet, you probably heard about, but the UNet was constructed in a very special way in order to learn the different, essentially learning different scales of the physics. Okay, with all the three ingredients, the morale is, turns out, customized design are very necessary. And this is actually surprised us in stark contrast and later on motivated us looking for other things. Because in many of AI fields, like computer vision, natural language processing, you probably realize you take one model, one architecture transformer, it seems to work everywhere. This is not true in this case. Okay, with all of these, the things actually worked out, secret sauce plus these ideas, and I will just present some numerical studies very quickly. Again, it's going to be light on details. We started a couple of flow problems, and we also benchmarked against a bunch of methods. Those are the data-driven approach, because we are interested in data-driven learning architecture, whether they can do this kind of emulations. Okay, this the left side is the typical eye candy thing, and each panel is different flow, and vertical axis is the time, horizontal axis is the space. Just eyeballing looks fine. Now we can actually time stepping the latent space, and it seems like the flow gets doing all right. On the right-hand side, we have a little bit more. In this case, we do some more quantitative metric and comparison. On this one, we computed relative root mean square errors, compare trajectory against trajectory. And the horizontal axis is roll out the time steps. And while actually our method over here, the red and blue one, actually outperform most competing method, we also found something disturbing, right? This is, again, now it's a common knowledge. As you're starting to roll out to longer horizon, you have a bigger errors accumulating. Now eventually you're going to blow up. Okay, so this is a common symptoms for all those data-driven approach at this present stage. What is interesting is on this particular flow, all other data-driven approaches just completely failed. Just very quickly, without rolling any decent amount of time, starting to blow up. Okay, so at least our approach start kind of doing reasonably well for a little bit period of time, then starting to get bad. On this side, I have similar things. Here we compare log energy ratio against the ground truth. Obviously, 0 is the best, and the closer you get 0, the better. And this is the horizontal axis now is the frequency. Now, the more frequency range you have, the better. And all the method here seems to eventually can fail when you look at the high frequency, that is the small scale features. Okay, on this particular flow, our method are probably the only method that actually able to do something reasonable. Everything else is starting to fail. Okay. All right. So what's the lesson I learned from this project? Data-driven approach actually works. The problem is long-term rollout stability was, and still remains a very challenging problem. Point-wise, RMSE, it's one of the workhorse of machine learning modeling strategy. Doesn't tell the whole story, right? It gives you some metric, but that's not all. We need to look at much other type of metric. In particular, small-scale patterns are really hard to get right. And probably the biggest one for us to realize that customer design, as I alluded to, is very much in need. Without all those nuances to different architecture or different training recipe, it's very hard to get it right. And discovering those robust recipe for general sets of problem remains a challenging problem. Now, going forward, we want to solve this problem, right? We want to solve this long-term stability problem. We want to solve this preserving small-scale patterns and features. How do we do that? And one default thinking, okay, maybe we shouldn't be so aggressive. Let's do something different. Let's add more physics to it. And hopefully there's a physics and equations that help us to preserve long-term rollout and to help us to preserve the small-scale statistics. And then now, since we're talking about small-scale features, maybe it's too much to ask to precisely recover it. Maybe we should think about how to model them statistically and focus on the quantitative interest in a statistical way. Okay? So in this one, I'm going to almost take a 180-degree turn. We're going to actually combining physics and equations very tightly and see how much progress we can make. Okay? So we're going to start this problem called closure modeling. We're going to start with Navier-Stokes equation over here, and folks are familiar with this. And in order to get the large scale of patterns, we're going to convolve with a kernel. It's going to give a bar U. This will be called the LES field. Now, for the LES field equation here, we can write down the equation, except we have this closure term. Unfortunately, the closure term models resolved the interaction between resolved and unresolved phenomena. So therefore, we cannot write it out analytically. Okay? What do we do here? Traditionally, we can try to come up with some ideas, closure models over here that only depends on the large-scale field, and hopefully it doesn't depend on unresolved scale, and this will be approximate the actual field, the DNS field. Now, for data-driven approach, the idea is pretty straightforward. If we have given the ground truth of desired filter field, we just come up with a machine learning model over here and optimize the heck out of this parameter such that the approximation closely track the ground truth. Okay? When we look at this problem, we decided to do something slightly different. We're going to take a probabilistic view on this. Now, instead of typically people using a deterministic view, using a neural network to try to optimize that closeness between the ground truth and approximation, what we're going to do to think about, maybe the desired LES field is ensemble mean of the corresponding DNS field. So it's a bit of a mouthful, so let me unpack a little bit. This idea stems from the work by Lanford and Moser about 25 years ago called ideal LES. The notion is the following. There are many DNS fields that if you do the filtering, they're all corresponding to the same LES field values, they're variable. Now, if you actually can keep maintaining these ensembles of DNS field evolvement, then you can construct uniquely, in many cases, an LES field such that this will be our ideal LES field. Right? You keep track of the mean. Okay? With that in mind, what we're going to do is try to rewrite the closure model in computing the expectation of this ensemble mean, the expectation of the ensemble of DNS field, and subtract to the equations with the filtered LES field. Okay? This is just a conceptually framing. It turns out algorithmically, there's a lot of challenge, remains. We actually don't know what this expectation looks like. We actually don't how to get to DNS information to begin with. So this is how we want to get rid of it, right? And this thing, unless you're dealing with a very simple system, is analytically just intractable. Okay? We're not making very far yet. But this probabilistic notion gives us some leverage. If something we don't know is latent from us, why don't we learn from data? So the idea comes from probabilistic generative modeling. What we're going to do is to learn to generate a distribution, try to match or emulate the real but unknown DNS fields distribution. Okay? So this is a figure we see on the previous slides. And here is the neural net. This is the learning architecture diagram. The bottom here is a still LES space, and top of that, what we call is a latent space. Sometimes in the paper, we refer to as studio DNS space. What we will try to achieve is very similar to the previous project using deterministic neural network for emulation. We're going to go through an encoder in the LES representation, and instead of using a deterministic neural network here, what we're going to do is having an ensemble of a trajectory. And those trajectory are going to do time stepping in this latent space. And at the end of that, we're going to go through the decoder. We're going to get back to NL space. And then we'll take a mean. That will be our NS field, as if we did the time stepping. Okay. And how to get this? We're going to use something called neurostochastic differential equation, NeuroSDE, to parameterize the trajectory over here. So the Z here is our latent representation, and this NeuroSDE is nothing but its regular stochastic processes, and you have a linear process here, except the drift and the diffusion coefficient are parameterized by neural network. Okay? With that in mind, you think, oh, there's a whole lot of machinery just for doing this, right? Turns out the learning problem towards the end is quite simple. It's actually a very minor change to the previous approach on deterministic neural network, and you can actually differentiate through this stochastic process as if you were differentiate through a regular neural network. So I'm gonna, omit the details, and I'm gonna present some, again, quickly, some numerical studies. This is the Kolmogorov flow, and on the left side is our, old friend comparing RMSE on the trajectory on different number of steps roll out. And I should mention that on this flow, rolling out to like a couple hundred steps beyond, you already end up in the regime of turbulence. So any RMSE comparison at that moment is become not very meaningful. But nonetheless, as a sanity check, this bottom one, magenta color, is our approach called the Neuro Ideal LES. And this middle one, orange one, is implicit LES. It's a classical numerical approach for doing LES. And the top one, what particularly interesting top one is, if you take out the neural stochastic differential equation, just replace the deterministic neural network, you're going to get the top one. And look at the gap between our approach and the deterministic one. In fact, we improved quite a lot by introducing stochasticity into the system, into the modeling. And if we compare to implicit LES, we're actually doing better than the classic numerical method. Now, as I said, this is just a sanity check. We can also compare them on the energy spectrum. Right? So again, this is the blow up as the high frequency regime. And this is the blue one is deterministic approach. And this orange one is the classical numerical method. In fact, it's actually for short on this. And we are comparing to the DNS, so therefore we almost perfectly recover the DNS solution. And this is some eye candy for this flow. I mean, the whole point is to show that and this is the reference, ground truth, and this is our approach, and we can preserve some small-scale features. On the other end, traditional numerical method, implicit LES, essentially become very diffusive. Therefore, all the small-scale features have disappeared. Okay. What is the lesson I learned from this? It seems to be very beneficial to have a hybrid physics ML method. It does. This integration does improve robustness of rollout. We didn't completely solve the blow-up problem, but at least it made it looks better. The probabilistic generative models is advantageous than deterministic model. Almost for sure now, we realize it can preserve energy spectrum well. It can actually roll out better. Now, what is the next step? Let's think about this, saying, oh, maybe we took the 180-degree turn, maybe too much. Maybe we should go somewhere in the middle. Or maybe we should just stick with our old idea, going back to the first very original idea. Let's focus on data-driven generative to see how far it can go. In some way, what we want to do is reduce the interdependency between the ML method and the physics equations. Can we achieve that? So now I'm going to talk about the third project. It has a very different flavor now. It's our current project, learning generative model outside of equations. As I mentioned in the previous one, to think about why we want to reduce the interdependency. In the previous one, we have a coarse numerical solver where the neural network or the probabilistic model is supplying corrective flux to the numerical solver. This is both a good thing and a bad thing, right? If the neural network will make a mistake, then the numerical solver would continue to carry on this mistake. It may actually bring instability because that mistake getting feedback to the neural network. And maybe we should disengage that. But how do we do that? So suppose we have low fidelity biased simulation by some solver. What we want to really get to observation that is a high fidelity simulation. How do we go that directly? Only one way. We don't feedback. Is that possible? You were wondering from low resolution to high resolution, it's just a supervised super resolution problem, isn't it? But turns out it is not. So this is sort of in some of the areas called statistical downscaling. So I'm going to explain why this is not just a supervised super resolution problem. And the blue one is the ground truth. It's low resolution, but nonetheless has all the right stuff in there. It's missing the high frequency component because of low resolution, but nonetheless, in the low frequency regime, you have the energy spectrum correctly. On the other end, for low resolution, low fidelity simulation, not only you are missing high frequency component, you also in the low frequency regime, you have a bias. You have errors that is different from the ground truth. So therefore, in order just to go into low resolution, high resolution in this case, not just learning super resolution, but also you need to correct the bias as well as increase the resolution. Okay. Our approach actually also marrying two cool ideas from machine learning community. But to explain this, let's imagine what we're going to do is we're going to first identify a latent low resolution representation that is unbiased. Right? Then from this unbiased, latent, low-resolution representation, we're going to go to our high-resolution ones. So hopefully that will solve the problem. Now, for the first step, how do we actually take a biased representation and make them unbiased? How do we do this debiasing step? We use this idea called optimal transport. What we do is, suppose we have high-dimensional ground truth, high-resolution ground truth. We're going to first do downsampling. And in the downsampling regime, as I mentioned, we're going to remove the high-frequency component, but yet for the low-frequency component, that stays true to the high-fidelity simulation. And here, on this side, we're going to have the low-resolution but a biased sample. What we're going to do to match the distribution of the two, I omitted some of the detail. That's the rationale for doing this, mainly because it's unsupervised learning. Because of, it's not a supervised learning. And in order to match these two, we can only assume they are weakly corresponding. They are samples from the same dynamical system, but there's no correspondence at a snapshot level. So you cannot just training a classifier to do it. And to learn this mapping, what we're going to do is to learn under this optimal transport framework and to learn a map that is deterministic from taking every snapshot from here, transform into another snapshot. I'm not saying the snapshot is physical. I'm just saying the snapshot over here will look something very similar as if it's downsampled from ground truth. Now, many scalable optimization algorithms has developed in AI machine learning community to solve this optimal transport problem in a different context. It turns out to be very useful for our purpose. Later on, people also discovered that this optimal transport is closely related to some generative modeling popular technology, including flow matching, but that's another discussion. For the second step, we're going to use something probably more familiar, more in the headline, it's the diffusion models. Particularly, we have this low resolution but unbiased representation, and we just inverse the downsampling step to make them super high resolution. Now, you could, in this case, learn a deterministic mapping by supervised learning now, but why don't we do that? Instead, we're using a diffusion model, and diffusion model is a stochastic sampler. It gives the samples instead of a deterministic mapping. It turns out this thinking is advantageous because it gives us uncertainty quantification about the inverse mapping. It also gives us the samples that have been generated very sharp. Loosely speaking, particularly in this case, referring to small-scale features can be are not blurred and can be recovered. And I think many of you probably have seen these headline pictures of how the details of generated images can be. Okay. Then this is some eye candy on applying our approach to the common graph flow. And the input, as I mentioned, is biased, low resolution simulation. This is our method over here, and this is the reference example. And in the middle is various degrees of a different type of method try to do super resolution or downscaling. And if you look at that, our method doesn't look like the reference at all. In terms of good, that's actually a good thing, right? We never said that they should be the same. We only said in distribution, they should be similar. Nonetheless, compared to a bunch of other methods, if you look at these few methods, only focused on try to do resolution sampling to do super resolution, as you notice that they're actually quite similar to the original input, except it looks finer. Why? They carry the bias, and they never try to fix the bias. In fact, if you check the energy spectrum, okay, again, this is the relative. So the closing to zero means perfect match. And these blue lines are on the two different super resolution regime, our method that performed the best. They're closer to the zero. That means that they are distribution-wise, they are similar to the ground truth. Okay. Now we can take this idea and try apply to climate and weather for real-world application. This is slightly different from the previous projects. We didn't do debiasing step. Instead, we're trying to solve this following problem. In numerical weather prediction, having probabilistic forecast is very important for uncertainty quantification. And how do people do it? People typically take initial condition over here, just perturb it, and then you're going to generate ensemble of a forecast. And that ensemble forecast representing your uncertainty about the forecast. Now, if depending on your computational budget, right, you could end up running a lot of ensembles and generate a large ensembles forecast. Or if you don't have a lot of a computation budget, you won't be able to. So in fact, this is the trade-off. Given a computational budget, if you increase ensemble size, you would inevitably have to reduce the ensemble simulation resolution. This is indeed what happens in operational weather forecasting system. Now, what we hope to get is this sort of a blue line. Even you can increase ensemble size significantly, your resolution needs to be reduced. And we're hoping that generative AI technology or probabilistic modeling technology can fill this gap. And indeed, this is what we did. Instead of using the previous approach, but very similarly, what we're going to do is take two physics-based simulation forecast, use them as seeds, and then using a conditional diffusion model, exactly similar to the one when we did super resolution, and generating a large number of ensemble members using this conditional diffusion model. Typically, we generate more than 500. And just to put things in perspective, in operational weather forecasting, people only generate at best around 50. Why this is particularly useful? First, the ensemble being generating those samples, the procedure generating samples are very similar to real weather forecast. So if you want them to represent the true weather conditions, the general sample should not be blurred. It should be looks like it truly like a weather forecast. And this is the comparison. This is from NOAA's operational forecast system generated the global feature map, temperature map. And this is the one generated from our sample. They actually look quite similar to each other. Generating a large number of forecasts also allows us to characterize likelihood of extreme events accurately. And this is the case study of this July 2027 Portugal heat wave, and at the lead time of 7 days. So this is the star here is the observation of the true heat wave being observed. And those orange triangles are the output, 31 members of weather agencies' operation weather forecasting system. And we took two of them, the blue square. If you notice that all the 31, including this blue square, is pretty far away from observations. That's why it's all extreme events, right? And what we do is use our model generated 10,000 samples to fill the gap between the, building a density map. Each one of them is the green dot representing a particular forecast, about 16,000 of them. And we generate this on a cloud-based TPU in under 30 minutes, and that's it. And if you take a look at it, this because we can generate so many, it actually provided a better statistical coverage of this unobserved at the time extreme event such that we can compute its likelihood more accurately. Okay. So what is the lesson I learned from this project? It seems like generative probabilistic approach provide a very flexible trade-off between high-fidelity physics, statistic relevance, and computational cost. In both these two projects in the last vignette, we didn't actually incorporate physics into the learning or inference process per se. We sort of made them less coupled together. Instead, there's a weak dependency among them. In the first one, we just completely disengaged. In the second one, we just use them as a seed. And physics simulation is just running independently of a statistic sampler. This seems to be especially powerful because of this property amortize a lot of computational cost. So what's in the future? Right. Generative modeling has been proven to be particularly useful for our case, but the generative model has other problems too, right? How to model dynamics, how to model realistic dynamics has been a challenging problem. We are not addressing this problem yet. We're hoping to address them in the future, and I hope that actually can prevent the blow up. And if we can, are we at a stage to claim generative model is all you need? For people in machine learning, you probably know attention is all you need. It's a very famous paper, and now afterwards, attention is not all you need, and convolution is all you need, a bunch of them, but we are thinking whether generative model is indeed as a backbone part of a scientific machine learning modeling workflow. That's a methodology question. What is the true application? We want to tackle the hardest computation problems at the largest scale. This is the come out from our teams. Simulating TOPS fire is probably the second most damaging fire in California in the history. This is simulation we did. This is the largest stratocumulus cloud, about a couple hundred miles and 2 kilometers deep. And this is a strongly convective storm that if you look carefully closer to the ground, we even simulate the precipitation. This has all been run on billions of grid points on cloud TPU infrastructure. Now, we have generated the data. The question is, can we do statistical modeling on such data sets? Each one is huge, and we are very excited for this opportunity to work on this. Let me summarize our journey. And there are many works try to figure out what is the right interface between physics knowledge and statistical modeling. We tried 3 different flavors. We tried a data-driven deterministic approach. We ignore all the physics, but turns out, okay, we need a customized design. What I didn't tell you, in the customer design, many of them actually inspired a physics property of underlying flow. The second project, we look at hybrid physics ML with probabilistic generative modeling deeply coupled with a low-resolution solver. That seems to work very well, but also proved the utility of probabilistic generative models. In the third one, we went back to the data-driven generative approach, but we condition our physics. This seems to work even better. Okay, it's all very exciting. I don't know what the next generation would be, but I'm pretty sure there's going to be a lot of creative ideas. Continue exploring this direction, try to figure out that what is the right way to inject the so-called physics prior into machine learning models. As a final thought, I want to talk about some high-level thoughts. This is truly exciting time to advance using machine learning to advance scientific computing for unprecedented pace. Still nascent. There's a lot of things we don't know about, particularly under all kinds of different paradigm. They are just a methodology, and they've been tested on toy problem, and they've been tried it on almost a real problem, but we don't know a lot of things about their operating condition. What are they? As a machine learning person, I'm super excited by the methodology side of the opportunity because it presents unfamiliar and a new challenge for machine learning to make foundational progress. Orthogonal to this, in echoing the interdisciplinary nature of this this year's PASC 2024 themes. I also feel that by working an interdisciplinary team, we had a lot of friction points. We have different people. We talk a very different language. I remember it took me quite a long time to understanding this thing is unphysical. What do you mean it's unphysical, right? From machine learning perspective, everything is statistics. There's no such thing unphysical per se. For me, it was a big culture shock. So we need to break down this barrier. We needed to amend the philosophical difference, try to reach a common goal. One way to think about that is open source, rigorous evaluation, a standard benchmark. So this is a little bit of plug for our team's work in establishing Weather Bench 2 precisely to help machine learning and people on the climate and the weather forecast community try to reach agreement on what kind of data set we use, what kind of evaluation protocol we should use to evaluate different methodologies. With that, thank you very much.
First of all, thank you very much, Fei, for this very broad and exciting talk. We have time for a few questions, so please feel free. Yes, I think there are some microphones. You can, no, right next to you, somewhere on the, you could find a microphone. Yes, someone has given you the microphone. Why don't you start?
So before I answer any question, I have to say, I'm jet lagged. So, for all the questions I can answer, I will answer. For all the questions I cannot answer, I can just make up. Hallucinate under the jet lag.
You can also hallucinate, yeah.
Yes,
please, go ahead.
Okay, you can hear me? Yeah?
Yeah.
Yeah.
Okay, thank you very much. So I'm a physicist, and when we use Fokker-Planck equation to simulate or to have a part of the simulating or generating a new system, or new configuration in the system, we usually apply it to one or few correlated variables, and then the rest is not affected by the stochasticity. I did not catch in your talk if you are applying this diffusion to all the parameters you're looking at, or you have restricted set of parameters that you are allowed to diffuse.
So a wonderful question. So if I need to repeat, her question was, when we apply generative models, are we applying to a subset of variables or more broadly selected set of quantitative interests, right, broadly speaking? Now, this is a really good question. In our work, we do apply to all the variables. This is very similar to image generation. In diffusion model, you actually try to get all the pixels in. You don't just compute a few set of statistics to do diffusion model on that. So that's on the tactical level, we do that. But you do ask an interesting question, and I think in the second talk, when I look at this Suju DNS field, I think that's precisely the underlying spirit. In fact, we don't intend to recover the whole DNS field. That's just impossible. Instead, we only recover the statistics that are relevant to reconstruct LES field. So I hope that kind of answers your question. Yeah, good one.
Further questions?
Yes.
Yes, please.
Hi, can you hear me? Okay. So thanks a lot for the talk. Really impressive work coming from Google on weather prediction models.
Thank you.
You talked or mentioned a couple of times weather and climate prediction, but most of the results that you showed were like 7-day evolutions of weather models. And I'm sure you're well aware that a lot of the state-of-the-art weather prediction models that we've seen coming that are purely machine learning based really struggle to get long-term predictions that are reasonable, especially when, like with climate models, you need to run them for tens or hundreds of years. And I was wondering, trying to get you to talk a little bit more about climate prediction, what you see as the most promising strategies moving towards stable long-term prediction models and skillful models.
Very good question.
So wonderful. Just to rephrase the question, and the question was I talked about the weather and climate, but the results I showed is a weather prediction at 7 days. This is very well in predictability regime, right? The predictability regime is estimated, roughly speaking, by 14 days, and no operating system has been able to reach that 14 days yet. AI system have not yet either. But then the question is, how did you see in the future rolling out couple hundred years, as now we're in the regime of climate projection. Right? Now, this is the thing I like about doing research. It has a bunch of stochasticity in it. When I started this project with my team, we were actually interested in climate projection. Okay, we were thinking, okay, how can we use generative models and push forward to a couple hundred years of climate projection, because in order to account for uncertainty in climate forecast, you need to run hundreds of thousands of climate ensemble simulation, and it's just impossible, depending on the size as well as the long trajectory, right? So we were thinking about how do we amortize the computational cost of that. Now, we actually developed the technology first. Then we said, okay, we don't have data sets, right? This is terrible. We have this like a big, interesting hammer, methodology hammer, but where are the data sets to test it? Then we switched to the weather. So in the weather, there's a rich set of data sets to allow us to testing this methodology. And you are absolutely right. Currently, in fact, the methodology shows it does work. For the one I presented, it does work for 7 days. It also works for 10 days, but less satisfying. But you are asking a very scientific challenge question. A couple hundred years, can you do that? We are working on it. Check our website in about 2 months.
Okay, I think Fei has been very generous. He has said that you can grab him anytime to ask him questions. I think in the interest of time, because all of you have to get out of this room and go to your mini symposia rooms, this is quite a logistical exercise because there's so many people here. I think let's have a big round of applause for Fei, and then